Once upon a time, in the late 19th century, the scientific world was on the brink of a revolution that would forever change our understanding of the fundamental nature of reality. It all began with a series of puzzling observations that challenged the well-established laws of classical physics. Our story takes us to the year 1897 when the British physicist J.J. Thomson discovered the existence of tiny negatively charged particles called electrons. This breakthrough sparked a wave of curiosity among scientists, and they began to wonder how these particles behaved within atoms. In 1900, the German physicist Max Planck made a groundbreaking discovery while studying the radiation emitted by heated objects. He proposed that energy is not continuous, but instead quantized, existing in discrete packets or quanta. This revolutionary idea laid the foundation for what would become known as quantum mechanics. Building upon Planck's work, a young Swiss physicist named Albert Einstein made his mark in 1905 with his explanation of the photoelectric effect. He suggested that light can behave as both a particle and a wave, depending on the experiment, introducing the concept of wave-particle duality. The year 1913 witnessed another pivotal moment in the evolution of quantum mechanics. Danish physicist Niels Bohr proposed his atomic model, which integrated the newly discovered electrons with the existing framework of classical physics. Bohr's model successfully explained the spectrum of light emitted by hydrogen atoms, but it raised more questions than it answered. Meanwhile, the French physicist Louis de Broglie was inspired by Einstein's wave-particle duality and speculated that particles, such as electrons, could also exhibit wave-like behavior. In 1924, de Broglie's hypothesis was confirmed by a famous experiment conducted by two young physicists, Clinton Davison and Lester Germer. They observed the diffraction of electrons, which provided experimental evidence for the wave nature of matter. The year 1925 marked a significant turning point in the history of quantum mechanics. Austrian physicist Erwin Schrödinger formulated a mathematical equation, now known as the Schrödinger equation, that described the behavior of quantum particles as wave functions. Schrödinger's equation provided a powerful tool for predicting the probabilities of different outcomes in quantum systems. Around the same time, German physicist Werner Heisenberg developed a mathematical framework called matrix mechanics. Heisenberg's approach, based on matrices and observables, complemented Schrödinger's wave mechanics and offered an alternative perspective on quantum phenomena. In 1927, Heisenberg introduced the famous uncertainty principle, which stated that there are inherent limits to our ability to measure certain pairs of physical properties with absolute precision. This principle revolutionized our understanding of the microscopic world, emphasizing the fundamental indeterminacy at the heart of quantum mechanics. The next major milestone came in 1932 when the British physicist James Chadwick discovered the neutron, an uncharged subatomic particle residing within atomic nuclei. This discovery paved the way for further exploration of the atomic structure and the development of quantum field theory. In the following decades, a myriad of brilliant minds, including Paul Dirac, Wolfgang Pauli, and Richard Feynman, made significant contributions to quantum mechanics. Dirac's work led to the formulation of relativistic quantum mechanics, which unified quantum theory with Einstein's theory of relativity. Pauli introduced the concept of spin, an intrinsic property of particles, while Feynman developed his famous path integral formulation, which provided a powerful method for calculating quantum probabilities. The story of the evolution of quantum mechanics continues to unfold even today. Scientists around the world are tirelessly working to understand and harness the strange and fascinating properties of quantum systems. From the development of quantum computers to advancements in quantum cryptography and communication, the impact of quantum mechanics on our modern world is truly awe-inspiring. And so, the tale of quantum mechanics serves as a testament to the ever-evolving nature of human knowledge and the endless wonders that await us as we delve deeper into the mysteries of the universe.